Well, first of all, I would like to thank you all for coming. My name is Filip Lemic, and the title of my talk is Short-Term Trajectory Prediction for Full-Immersive Multi-User VR with Redirected Walking. And this is a collaborational effort between Internet Technology and Data Science Lab of the University of Antwerp and the Nano Networking Center of Catalonia. And I'm currently employed at the I2CAD Foundation in Spain. So let me start by introducing this work. So presumably the majority of us knows that virtual reality is essentially revolutionizing our digital perceptions and interactions. Well, VR finds applications and in healthcare, in tourism, in education, entertainment, and so on. The main research goals in domain of virtual reality are focused on enhancing the immersiveness of virtual reality experiences. And this is done along three main dimensions. First is enhancing the quality of video content that is being presented to the virtual reality users. By quality, I do not just mean the pixels, but also enabling kind of 6 degrees of freedom type mobility in contrast to 3 degrees of freedom type mobility, which is currently enabled in virtual reality. And you can see that at the bottom of the slide. So on the left-hand side, we have kind of a screen that is projected to the virtual reality user, and that is kind of represented with the 3 degrees of freedom in terms of mobility, because the user is only able to move his or her head. So only rotational movements are supported. While in the 6 degrees of freedom, the user is essentially immersed in a virtual experience. So it can move, it can rotate its heads, but it can also kind of move longitudinally. In order to be able to move longitudinally, we also need to cut the wire and enable truly wireless experiences. Obviously, wire is a tripping hazard. And then the third aspect is enabling multi-user experiences, in a sense that the remote users can share the virtual experience. They can immerse into the virtual experience jointly in a way that the action of one user is reflected in the virtual experience of the other. So presumably these virtual experiences, full immersive virtual experiences with 6 degrees of freedom, are going to be deployed in a physically constrained environment. Why? Because we need to kind of constrain the users in their movements, so otherwise obstacles in the environment become a tripping hazard. In order to deliver this high-quality video content, we'll have to switch from more traditional sub-6 gigahertz systems towards millimeter wave and above frequencies. Why? Because those frequencies offer large bandwidth that is able to meet the requirements of VR applications. At high frequencies, there is a high free space path loss, and such communication is can be significantly affected by the obstacles. So for these reasons, the energy of the millimeter wave signals is usually focused towards the desired directions, and we call that directional communication. So in order to focus the signals in the direction of the virtual reality users, intuitively there is a need to know their near future location so that we can essentially track the users with the beam. And this scenario that we are considering is depicted in the figure. So we can see that the access point is using high frequency wireless communication, directional one, for delivering the content to the VR users. The VR users are deployed, or they exist in a constrained physical setup, while their virtual experiences are potentially unbounded. So in order to avoid collisions between the users and the environmental boundaries, or between the users themselves, we employ redirected walking. Redirected walking is a technique of imperceivably re-steering the users in the physical space, while in the virtual space, they have a feeling of an uninterrupted virtual experience. So you can see how this redirection works in this slide. So on the left-hand side, we see 3 users being deployed in an unbounded virtual, or being immersed in an unbounded virtual experience. And we assume that they're walking randomly inside of that virtual experience. Well, on the right-hand side, you can see their physical movement trajectories. So, and as you can see, those physical movement trajectories are bound within a 5 by 5 or 10 by 10 meters large physical space. So the idea of redirected walking is essentially to map those virtual coordinates of the user towards their physical coordinates in a way that the collisions with obstacles, with other users, or with the environmental boundaries are avoided. So the idea here is to try to predict the near future physical coordinate of the VR users. So for this prediction, this is a time series prediction. There are two recurrent neural network approaches that are usually used. So one of them is a long short-term memory, LSTM, and the other one is Gated Recurrent Unit. I will not go into the architectural details of those two approaches, but you can find them in the paper if you're interested. So here we take the inspiration from the prediction of the normal human walk, so the near future trajectory prediction of the normal human walk, which is a challenging problem. But here we have redirected walking, which is kind of constraining the users in their movement. And by doing so, we intuitively believe that the prediction accuracy of such kind of redirected walking, like walking, is going to be higher than for the normal systems. So in essence, in our baseline solution, we used historical locations, historical physical locations of the VR users to predict their near future locations, as you can see here in the slide. So we have a black box machine learning approach. We have the historical coordinates that go from t minus n towards t, and then we predict for the next instance where the user is going to be. Now, since the redirected walking works in a way that the virtual coordinates are mapped to the physical coordinates under certain constraints, it is also intuitive that the virtual coordinates feature some information that can be used for enhancing the accuracy of that prediction. So for the accuracy enhancement purposes, we also consider a scenario in which a neural network, a recurrent neural network, is fed with the physical historical coordinates of the user, but also virtual historical coordinates of the users. And then the goal is again to predict the next step, so the near future location, physical location of the users. And this is depicted in this slide. For those two approaches, then we carry out the hyperparameter tuning, which would mean we set all of the hyperparameters of the LSTM and GRU networks to some default values. Then we select one hyperparameter, we vary its values across a number of potential values, and we try to find a value for which the mean square error is minimized. And we carry that out for different hyperparameters, including number of neurons in the LSTM or GRU layer, hidden layer, or the optimizer functions such as ADAM, NADAM, ADAMAX, etc., activation function, number of batches and epochs, and the learning rate. Now, we utilize a simulator that is depicted at the top part of the slide for simulating the mapping between the virtual coordinates of the users and their physical coordinates in the constrained space. The simulator is able, given the input, which is depicted here in the picture, generate an output, which consists of the physical trajectories of all the users, number of hard resets, meaning observable resets, re-steers that can be observed by the users, distance between such resets, and the metric that you're interested in, and this is the accuracy of short-term trajectory prediction. Here are some parameters of the simulation. We do sampling across the trajectory. We select 10 points per second of the movement of the user, and the duration of the whole simulation is 1 hour in the real time. There are also some parameters related to the redirected walking, and here on the right-hand side in the table, you can see what are the optimal hyperparameters of different approaches. And the approaches that we consider here is the LSTM baseline, LSTM with virtual coordinates utilized in addition to the physical coordinates, and same for the GRU networks. And here you can see a snapshot of the results. As visible in the results, so this is the squared error for the LSTM prediction performance, and this is the square error for the GRU prediction performance. As you can see, the LSTM outperform. So LSTM, when utilizing virtual coordinates in addition to the physical coordinates, outperforms the baseline as visible from the figure here. We also define, and similar can be observed for the GRU network. We also define a set of intermediary approaches where we distinguish them based on the in intermediary one, which is this one here and this one here, we use the same hyperparameters as the ones that are used here in order to isolate only the effects of utilizing virtual coordinates. And this is depicted here. For the intermediate approach 2, we utilize the same hyperparameters except for the number of batches and epochs, which is doubled in comparison to the baseline approach. And this is done in order to better deal with the complexity that is introduced due to the introduction of virtual coordinates as an input feature for prediction. And as we can see, there is a kind of stepwise decrease in the square errors, suggesting that the optimally hyperparameterized network utilizing virtual coordinates is the best performing one. There is obviously a trade-off, and this trade-off comes in the latency. So as you can see, there is an increase in the execution time due to the introduction of the virtual coordinates in the systems for both GRU and LSTM networks, though this introduction is rather small and mainly focused on the training part, not really on the execution part. And then the next snapshot of the results depicts the performance of the redirected walking system as we introduce more and more users in the shared physical space. And you can see on the x-axis for both LSTM and GRU, you can see on x-axis the increasing number of users, and then you can see the performance metric that we are able to capture with the mentioned simulator. So in terms of the number of observable resets, so kind of interruptions in the immersiveness of the experience, as we introduce more users, we observe an increase in the numbers of such resets. And this is going from less than 400 resets inside 1 hour to more than 500 resets as we increase the number of users from 1 to 8. Similar can be observed with the distance between consecutive resets. Intuitively, the distance decreases, the users can traverse less space without being observably re-steered. Interestingly, the short-term trajectory prediction performance is not dependent on the number of users. And this is a beneficial indication. It indicates that potentially we will be able to train a neural network, or either LSTM or GRU one, for a short-term trajectory prediction for a single user, and then use this predictor across a different set of users. And this is it. Let me just conclude the work. So in this work, we have considered LSTM and GRU-based recurrent neural networks as candidates for the near future movement trajectory prediction in multi-user full-immersive VR setups with redirected walking. We advocate utilization of virtual context, so virtual movement trajectory, as an input feature for such predictions. Our evaluation results suggest that the predictor, once trained assuming a static number of users, can maintain the accuracy for a changing number of users without the need for retraining, which is an interesting observation. And future work will be focused on experimentally assessing the derived insights. And this is it. I would like to thank you for your attention. And if you have any questions, please ask.